we were discussing about inner product spaces, and we have also seen the concept of orthogonal sets and orthonormal sets in vector spaces. Orthonormal sets were orthogonal sets whose elements are unit vectors. Now we also seen that orthonormal vectors are linearly independent, and I have given an example to show that linearly independent sets need not be orthonormal, but from every linearly independent set in an inner product space, you will be able to construct an orthonormal set. And that's what is done by a process called Gramm-Schmidt orthonormalization process. So we will construct an orthonormal set from a given linearly independent set, and we will be verifying that it is orthogonal set, and we will be forming an orthonormal set from an orthogonal set by dividing the vectors with their corresponding norms. Okay, so let v1, v2, etc. Vn, Vn, n elemented linearly independent set in an inner product space capital V. Now you define y1 equal to v1 itself and take y2 as v2 minus inner product v2 y1 divided by inner product y1 y1 times y1. Now there is a geometry behind the construction of y2 from y1 that can be seen when you consider three-dimensional vectors. In R2, you consider two vectors v1 and v2. So suppose this particular vector is v1 and this particular vector is v2. So they are not perpendicular, they are not orthogonal. So I want to create an orthogonal set from this collection of v1 and v2. So what I do is I'll call the unit vector in the direction of v1 as v1 cap. Now you take y1 as v1 itself, because the first vector which we want to start with can be taken as any vector. So you take it as v1 itself. We want a vector perpendicular to this y1, right? That means you want a vector in this direction, in this perpendicular direction too. This is the direction of v1. So what I do is I'll take the projection of this vector v2 onto v1. So that done by taking v2 dot product or inner product with the v1. So this will be giving you this projection of v2 onto v1. So this particular length, which I see that this particular length is inner product of v2 with the v1 cap, not with v1 cap. Now that's not a vector, so if you want to make it as a vector, you have to multiply with the v1 cap. You multiply it with v1 cap. So this particular vector is obtained. So this is the vector v2 v1 cap times v1 cap. Now this particular vector is v2, and this is this particular vector is v1. Now what I do is, let us call this this particular vector as b, and we will see what is b. You can see that b is perpendicular to this. This particular vector is perpendicular to this v1 or y1. Now what is b is the question. Let us call this v2 v1 bar as a bar. So this vector is a bar. Then you know that a bar plus b bar is equal to v2 or v2 bar, whatever you can call. So b bar is what? B bar is v2 minus a bar, right? So that's equal to v2 minus, what is a bar? A bar is the projection of v2 onto v1. So what we have is inner product of v2 v1 bar times v1 bar. Okay. Now what is v1 bar? v1 bar is just v1 divided by its length, because it's a unit vector along the direction of v1. So it is nothing but v2 minus inner product of v2 with the v1 by length of v1, that's the unit vector v1 cap, into v1 by length of v1. So that is nothing but v2 minus 1 by norm v1 is a constant, it can be taken out of the inner product. So 1 by norm of v1 into inner product v2 v1 times v1 by norm of v1 is again there, so I'll put it as square of this norm v1. So you have this v bar is equal to v2 minus inner product of v2 v1, which is a scalar, divided by length of v1 square. That is nothing but inner product of v1 with the v1 times v1. Or in since I have taken v1 as y1 itself, You can say that this is V2 minus inner product of V2 with Y1 divided by inner product Y1 with the Y1 itself times Y1. So this is how this formula has been arrived, the second one from the first one. Okay. Similarly, Y3 is equal to V3 minus, you have to reduce both the projections in the direction of Y1 as well as Y2. So V3 minus V3 Y1 divided by Y1 Y1 times Y1 minus V3 Y2 divided by Y2 Y2 times Y2. So this is a scalar multiple of Y1 and this is a scalar multiple of Y2. This is actually the projection of V3 in the direction of Y1 and this is the projection of V3 in the direction of Y2. So they have to be subtracted, etc. Yn is equal to Vn minus inner product of Vn Y1 divided by Y1 Y1 times Y1 minus inner product of Vn Y2 divided by Y2 Y2 times Y2 minus etc. minus last term will be inner product Vn with Yn minus 1. Just before Yn, here Yn minus 1 will be defined. So inner product Vn times Vn with the Yn minus 1 divided by inner product Yn minus 1 times Yn minus. So this is how we construct the collection Y1, Y2, etc. Yn. Now we have to show that these are forming an orthonormal set. I will show that inner product of Y1 with Y2 is equal to 0. Inner product of Y2 with Y3 equal to 0, etc. What you do is you take inner product of Y2 with Y1. Now by definition Y2 is what? 2 minus inner product V2 Y1 divided by Y1 Y1 times Y1. This inner product can be splitted into 2. So inner product of V2 with the, due to the distributive property, just inner product of V2 with Y1 minus, this is a negative sign, right? So minus inner product of the scalar times Y1 Y1. Now the scalar is coming out of the inner product like this. So inner product of V2 Y1 divided by Y1 Y1 is a scalar. So that will come out of the inner product like this. And what remains is inner product Y1 Y1. Now this inner product Y1 Y1 and inner product Y1 Y1 will get cancelled. So V2 Y1 minus V2 Y1, this is equal to 0. Similarly, you can show that inner product of Y3 with Y1 equal to 0, etc. Inner product of In with Yj is equal to 0 for every Ij. Thus we get the collection Y1, Y2, etc. Yn, which has been created using this process, an orthogonal set. Now how to make it as an orthonormal set is, you just take the vectors and divide by their norms. Then you get an orthonormal set. None of these vectors will be 0 because this collection is a linearly independent set and linearly independent sets will not contain zeros. So whatever you create also will not be containing 0 because these will be also linearly independent. So you define U1 is equal to Y1 divided by inner product Y1, U2 is equal to Y2 divided by inner product Y2, etc. So as in this, that's a standard process by which you can create an orthonormal set from a given linearly independent set. And you can also see that the span of V1, V2, etc. Vn will be the same as the span of U1, U2, etc. Un, because you have taken U1 as V1 itself, U2 as V2 minus some constant times V1, right? So it's a linear combination of V1 and V2. So Y2 is nothing but a combination of V1 and V2. So whatever can be created with the V1 and V2 can be created using U1 and U2. And similarly, you can see that the span of V1, V2, etc. Vn are nothing but the span of U1, U2, etc. Un. Suppose this is a basis. Suppose this V1, V2, etc. Vn is a basis. You start with a basis. Basis is always a linearly independent set. And from a basis, you can also create an orthonormal set. And that orthonormal set will be a basis as well as an orthonormal set. And that is called an orthonormal basis for a vector space. From a given basis, you can apply the Gramm-Schmidt orthonormalization process to get an orthonormal basis. Now let us see a simple example in R3. I am taking three vectors, v1 equal to 1, 0, 0, v2 equal to 2, 2, 0, and v3 equal to 0, 1, 1. These three vectors are linearly independent. So I want to create an orthonormal set from this. So y1 is equal to the v1 itself. v1 is 1, 0, 0. So y1 equal to v1. y2 is equal to v2 minus v2 is 2, 2, 0 minus inner product of v2 with v1, v2 with y1 divided by inner product of y1 with y1 times y1. So this is 2, 2, 0 minus this is 2, numerator is 2 plus 0 divided by denominator is 1. So 2 into this is 2, 0, 0. So if you subtract, you get 0, 2, 0. Now third vector is y3 is equal to v3 minus inner product of v3 with the y1 divided by inner product of y1 with y1 times y1 minus inner product of v3 with the y2. y2 is this. So 0 to 0 divided by inner product of 0 to 0 with the 0 to 0 times 0 to 0. Now this is 0, right? This numerator is 0. So the first vector is 0, 1, 1 minus second vector becomes 0 minus third vector is having 0 plus 2 plus 0, that is numerator is 2 and denominator is 0 plus 4 plus 0, so denominator is 4. 1 by 2 times 0 to 0, so 0, 1, 0. So if you subtract, what you get is 0, 1 minus 1 is 0 and 1. So this is your y3. Now you define u1 equal to y1 by length of y1, that is nothing but 1, 0, 0 itself because its length is already 1. Now y2 is 0 to 0, so u2 is equal to 0 to 0 divided by the length of 0 to 0, that is 2. When you divide it, you get 0, 1, 0. And y3 is a unit vector, so y3 same as u3. u3 is equal to y3 divided by length of y3, but length of y3 is 1 itself, so 0, 0, 1. So from a given non-orthonormal collection of vectors, which is linearly independent, you can create an orthonormal set u1, u2, u3 like this. This is the Gramm-Schmidt orthonormalization process. Thank you.